Let's solve this given homogeneous differential equation. We are lucky to see here an equation already involving the differential operator d. And with this in mind, our dependent variable is of course given to us as y. Please take note of that because that will be part of our solution later. Now, just a disclaimer, this video already talks about our solutions or our roots later that will be under the auxiliary equation are already distinct and real. But for some cases, it's not given. It's just that here, it already identified that the roots are distinct and real. That's just one of the four possibilities, because the other three possibilities is the second one is what if the roots are still real, but some of them are repeated, or we have multiplicity of 2 or 3. The third situation is when our roots are imaginary, and the fourth one is our roots or some of our roots are imaginary at the same time there are multiplicity or they are repeated. In this case, we are assumed already that the roots here of our auxiliary equation are distinct and real. And at the same time, our given is already an equation using differential operator. Hence, we just can automatically transform it into an auxiliary equation f of m. And that would be m cubed minus 2m squared minus m plus 2 equal to 0. The goal here is to solve for the roots of this given auxiliary equation. And with that, we can use here all the necessary methods. Now, this is a cubic function, so the quadratic formula will not be used here because that's just for a quadratic function where the highest degree is 2. So what we can use here is the rational zero or the rational root theorem in factoring polynomial functions or polynomial equations rather. This is only possible when our coefficients are all integers, and we know that the coefficients here is 1, -2, -1, and 2. The rational root or rational zero theorem tells us about a certain p over q, where p are factors of your constant 2. The factors are 2, 1, -2, -1, and your q here are actually the factors of your first coefficient, so 1. So it could be 1 and -1. You take all ratio of p over q and you try all of them here. But for some cases, it would take a lot of time, especially if your constant here is greater than 10 or even a very large value. So the rational root, rational zero theorem may be a help, but there are also some instances that you need to think intuitively in solving this. I'm just mentioning that because for some, just to remember that there is always that strategy that we can always apply when solving for the roots of a polynomial equation. The other strategy that we're going to introduce here is the idea of the intuition, at the same time the use of the syntactic division. If you're going to think of a certain number or a certain value for m, that when substituted here will be equal to 0, you can automatically use that for our first factor. The first value of m that you could try here is when m is -1. Okay? When m is -1, it's equal to 0. Checking. When you do it like here, that's -1, the cube of -1. Then minus 2 times the square of -1, minus -1, and then plus 2. This is -1 minus 2 plus 1 plus 2. Definitely that's equal to 0. That's one thing that you can try. And of course, going back to rational root or rational zero theorem earlier, this value of -1 is possible value of p over q. We simply tried that. Now that we are sure of that, we can now look into the next solution. As of course, if m is equal to -1, your first factor here is m plus 1 equal to 0. Now looking into this, let's try to check what would be the next value when this is divided by m plus 1. So you will have syntactic division here, 1, -2, -1, and 2. And your c here is, as mentioned, -1. Okay, so syntactic division, review that. 1. 1 times negative 1 is negative 1. Add, that's negative 3. Negative 3 times negative 1 is 3. Add, you will get 2. 2 times negative 1 is negative 2. Add that 0. You would know that this is really correct when your final value here, your remainder, is 0. Okay, that's why it's called the rational 0. One of the roots of our polynomial equation under rational root or rational 0 theorem. Hence, after dividing the auxiliary equation by m plus 1, our next form of equation is m squared minus 3m plus 2 equal to 0. Now, you can always use another trial at the same time, of course, select division, but since it is a quadratic equation, you can always factor that using quadratic formula, or also solving for the roots using quadratic formula, or by factoring. The factors here, if you were not able to master that, AC is 1 times 2, so that's 2. The factors of 2 when added will result to negative 3, is simply negative 2 and negative 1. Negative 2 times negative 1 is positive 2, but when you add them, that's negative 3. Hence, these are the values of your coefficients paired with m minus 2, m minus 1 equal to 0. So all of these 3 are the factors of our auxiliary equation. Hence, you will have something like this. Let me erase this factoring easy method here. Please review that as well in your own time. So your auxiliary equation can be written like this. You have your first factor m plus 1 earlier by intuition and proven by your synthetic division. Then you have m minus 2 and m minus 1 equal to 0. So according to the zero factor or zero product property, m plus 1 equal to 0, your first root is negative 1. M minus 2 equal to 0, their second root is positive 2. And m minus 1 equals 0, your third root is positive 1. Okay, so we have now these 3 roots, and that's the truth. They are distinct and real. They are different. Now, once we are sure of the roots, let's now provide the solution for this given equation. The solution is under using your dependent variable. It's expressed in this manner. The general solution when our roots are distinct and real is y is equal to your first constant, any constant, e to the power of m1 times x, plus your second constant times e to the power of m2x, plus dot 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 plus cn, if there are n possible of roots, e to the power of your mth root times x. So since there are 3 of them, we expect to have 3 terms here, and we will end up until c sub 3. So your solution here is in this manner. Y is equal to any c sub 1 that you can think of, e to the power of negative 1x. That's our first root here. Plus c sub 2 times e to the power of your second root 2x. Then plus c sub 3 e to the power of your third root 1x. This is the solution of the homogeneous differential equation using this process. As mentioned in the previous video, this could be interchanged. You could have 2 here, this would be your 1, this is your negative 1, even if not interchanging your constants because they are arbitrary constant, but it doesn't matter, it's just the same. But for the purpose of the presented roots earlier, we started with negative 1, then 2 and 1, so we arranged it in this manner. Thank you very much for watching.